please. Professor Franz from Paderborn University has been here quite a few times, actually. And you have seen he's quite active in this collaboration between Brazil and Germany also. There is a funding mechanism between Germany and CAPS in Brazil, and he's the guy from Germany who runs this cooperation, and he has worked a lot in his adaptive embedded systems. So we have some students from mechatronics here and also computer science. I think they are quite interested in the things you're happy to say.
Yeah, thank you very much. So I remember that I've been in this room a couple of years ago when celebrating Professor Macedo's distinctive, the anniversary of his distinctive institute. It was 10th? Or? Okay, the laboratory. Okay. What I would like to speak about today are digital twins and the role in engineering. So just to give an idea what digital twins are good for, it's a slide from the Technical University of Denmark and deals with windmills. So you see the blades are built, and as any kind of engineering means, you produce documents. Of course, a numerical model of the blade is constructed as well, otherwise it would be impossible to make the blade. In reality, in the production process, there will be some defects. That's unavoidable, and now it makes sense to have to model these imperfections in the model as well. And then, when being deployed, some more defects can happen. For example, in Europe, you may have hailstones. I think you don't have them so frequently here, which may cause some damages. And again, you can model these damages as well. You deploy anyhow sensors along the blades, and with the information, and that's important, the exchange of the continuous exchange of information in between the physical reality and the model allows us to have a numerical modeling of the defects, knowing the information from the sensors. We can then experiment with repairs for these defects and play them back to the real blade. And with the sensors, we even get the feedback whether this repair was successful or not. So just to give you an idea what digital twins are good for. And that's the outline I want to speak about. I will try to define what is a digital twin, speak a little bit about the design process and modeling techniques. We want to have executable models, so I have to speak about execution engines, and then some application areas in around cyber-physical systems. So there are, as whenever in computer science, when we invite some buzzwords, there are dozens of definitions, what we shall understand. So let me try to use a definition by these authors here. They say a digital twin is a dynamic virtual representation of a physical object or system across its lifetime. That's important. So we do not end by engineering. It's across a lifetime using real-time data. We are seeing that the sensor information is fed back to enable understanding, learning, and reasoning. And so that's a nice picture by Siemens. You see this digital twin following the physical car. We have this in a couple of engineering disciplines. Interesting enough, the civil engineers now are very active in a field which they call BIM, the Building Information Modeling. And again, it includes all aspects of planning, building, financing, maintenance, whatever you imagine is included in this model and all the parameters and the interrelationships. So that's a way they can more efficiently design and operate complex buildings. This year we celebrate 500th birthday of Leonardo da Vinci, and this brings us back to modeling. So of course, whenever you are doing engineering, what is engineering? And engineering is the process to create documents and to modify them. And so you see here some model, non-electronically readable, of course, but a model of some engineering object. Something is strange here. Let me see why. Ah, okay. So it's the wrong way. It's not my own computer, and therefore the animation works not properly. So I wanted to go from left to right. So just historical points of view. So in the beginning of traditional engineering, engineering documents are not available in digital form. They has to be interpreted manually, and modifications of documents means hard work, as you see here. It becomes better if we are in engineering with digital documents. They cover the entire design phase and could control the manufacturing and partially are executable, but of course the remaining life cycle is somehow supported by these digital documents, but not completely. And the consequence, the next step then are these digital twins digital documents for the entire life cycle. So they have to be fully executable with arbitrary precision and has to consider physical real-time data going back from the sensors to the document. And this enables them to support also aspects like safety and security, adaptation, optimization, and supporting the everyday operation of the objects. There are a couple of properties of digital twins. I don't want to read them all. But again, what's essential that they continuously exchange information with the related physical object. Now, let's look at modeling techniques. The main modeling techniques we are using in computer science today are either or both of them object-oriented engineering and aspect-oriented engineering. So in the object-oriented engineering, we partition our problem into different objects which mutually influence each other. We are providing the underlying models at various levels of abstraction. And so we can cover by this the structure of a system based on objects, as well as the behavior based on the behavior of the objects. And what's important, we are making a distinction between object classes and instances called objects. In aspect-oriented engineering, we look mostly what we are interested in. So we decompose a system into various concerns, the aspects, and we try to consider this concern separately. And so in aspect-oriented modeling, we have to identify, specify, and represent all these cross-cutting concerns and their modelization into separate functional units. Of course, what we need is an automatic composition into a working system, especially with the correct weaving of aspects. So these are the basic modeling techniques we are using. Next step is, if we have just a model, we want to bring in life into it. So we have here a model, which is static, and then we have an execution engine, which makes this model an executable one. So for making a model an executable one, we have first of all to classify the information which we find in the model into static data, mostly called parameters. They remain the same over lifetime in the model. And dynamic data, we call the variables, which changes during lifetime more or less frequently. And executing means that we add this execution engine, we bring in a time dimension, and the inputs are external inputs, triggers, and the current value of the dynamic data. And the output is then the next value of the dynamic data and external outputs. So we see it here again, when this digital twin consisting of static data, parameters, dynamic data, the variables, and computation instructions how to handle the dynamic data. And then the execution engine follows these instructions and calculates based on the current value of the variables the next one. So either by differential equations, we are some function of the current value, the derivatives, and the inputs, or here you see the notation which we have in discrete system in finite state machines, where we have the next state of the system composed, calculated from the present state and the input. So that's a very old idea. It goes back to the theory of differential equations, and has been applied in various ways to various areas. We have two classes. We have stabilizing systems which converge towards a stable state, and it can be distorted only by external triggers, or we have inherently unstable systems which can be interpreted as self-triggering systems. Just to give an example, gate logic. So this here we have a representation of a function. This Q is always, at any point of time, it is a function of values which we had at the input sometime earlier. And what means sometime earlier is part of the specification of the used gates here. But it's important to mention that this is an equation. This is always a function of the input. Sometimes it is complicated to explain students that the way we are calculating here the equations, the individual equations, is irrelevant. It has, it's not necessary to calculate this first and then this, as the entire, it is a combinatorial circuit, is just a function. It's a function over time. Another decision which we have to do, well, in theory, it is possible to have one single universal digital twin. And we can provide a model and the execution engine for each level of abstraction at each aspect. So whatever we are interested in, this all may be a part of this universal model. This would be bloodily inefficient. Therefore, usually one works with families of digital twins, where each member is dedicated to a specific level of abstraction and a specific aspect. Then, of course, we can optimize the calculations of problems to be solved. However, there's never free lunch. We have to pay for. The question is to keep the models consistent, and we have to look at these interdependencies of the various aspects. So we pay by management effort for gaining efficiency in execution. already mentioned feedback, and we find this feedback in very different layers. So the target object in engineering, in most cases, it is a system with closed loop feedback. We have seen the design process itself can be seen as such a feedback loop. And even the development of design processes, next meta layer, can be seen as a feedback loop. So here we see a design, and unfortunately it's not so clear. What you see below is that after having a design process, we rate it, whether it is fulfilling our requirements or not, and if not, then we are even able to repair the design process. This brings us to this example, but let me, I think, I always tend to be late, so I will skip this picture here. It just gives you various levels of for feedback in the design. So what are digital twins good for? Just to mention 3 application areas. One is safety. They allow us to pre-simulate future states. They allow us for online model checking. I will explain what this means. And we always can compare the model versus reality. In security, they may be helpful as well, as we have IoT, Internet of Things. This implies, of course, security risks, as we are connected to an unsafe ecosystem, the internet, and connect very subtle and safety critical objects with them. One way may be to encrypt any problematic data, but that's problematic due to limited computational power of the controllers. There is research going on encrypted controllers, which are doing all the control calculations based on encrypted data. At the moment, this is possible only for very restricted classes of functions. An alternative may be that all external signals are filtered by this digital twin, which runs on anywhere in the cloud on computers with much higher computational power, and it is there decrypted and sent to the real object. But now we have to make the assumption that we have a safe channel between digital twin and physical reality. So whatever you do, it's not so simple. A third application example might be self-adaptive systems. So we are transferring the design process to a certain amount into the operational phase. And if we have real IoTs, then we are forced to do this. The environment will change over the lifetime of a system. I mentioned online model checking. What is the idea? Here we are in the model, an abstract model, and we know there might be a couple of initial states, and then we can execute it in the model for some steps into the future. Now the good news, this is a digital twin, so we know in which state our physical object is. And we can abstract this state into an abstract state one, and now we know what starting state we are starting in the model. This restricts dramatically the search space which we have to cover in our model checking. So these are now the possible states which we may reach after certain steps, and if we have our requirements, say, sketched here by two boundaries, as long as we inside the boundaries, we say, well, what's going on here is safe, the system can operate in this way. And then we can continue in this. Step by step, so we are not proving that our system is correct. We are only checking whether our system, within a short time into the future, will operate in a safe in a safe corridor. I mentioned cyber-physical systems, which means that we are combining two things which are completely independent by tradition: embedded systems, highly dependable, predictable, and on the other hand, the cloud, a chaotic system which can be characterized mostly with probabilistic methods. So we bring this strict world of real-time computing in connection with the cyber phase, which of course causes a lot of problems as we are combining two worlds which in the beginning do not fit, and even the communities doing research do not know each other. And one way how to solve it, that we say, well, we are following this idea of online model checking. We do not require that a system needs to be always correct. It has to make local guesses, and if we at some time we get the global information, we can check whether our local guesses have been correct, and if not, then we correct. As we depend in IoT on channels with non-guaranteed runtime, so we can never guarantee that we have the most recent information about our environment. And so that's the only chance to make guesses and repair if necessary. And the digital twin will help us. Let me skip this. The digital twin can help us, and I will, and I'm coming to the end, shortly explain how another feedback loop, you see I like feedback loops, it goes back to work by Mary Shaw, describing such adaptable systems as in this way as a feedback loop. So first of all, we have to find out whether it is necessary to adapt. And that means we have to check whether our objectives are still met by our embedded system and the operating environment. So we have to model both. And so we have a model of the current and future states, and we have to check whether our objectives are still met by this. And this can be done by model checking. So we have our requirements, what do we want to achieve, our assumptions, which is nothing else than the model of the environment, and from this we should be able to conclude the specification of our system. And if this fails, the only point where we can play with is our specification, the model of the embedded systems, as the environment is given, and let's assume at the moment that our requirements have to be fixed as well. The transformation from the specification to the implementation is assumed here to be to happen automatic. And the way how to make this check is already explained. It is this trick of online model checking. Now let's assume that we did find out we have to do something. So next what we have to do is to plan the adaptation. You may have read this MAPE architecture from IBM describing a very similar loop. I give only some ideas. We assume that we have some ecosystem where we in the web we have available components which we can collect automatically to a system to solve our problem. And we have a rather large project running at our university how to do this, how automatically compose from an ecosystem of components the resulting system, and what components to select. Well, we can use the counterexample provided by the model checker to steer this selection process. But now we are confronted with the next problem. We have to effect the adaptation, and we have real-time systems. So we must be sure that what we has as a result of the adaptation is consistent with all the real-time requirements which we have. And even the repair process itself runs under real-time constraints. Again, this works from my point of view only if we restrict ourselves on a fixed ecosystem. And our ecosystem consists of classes of components. And in each class we may have one or more objects for this class. So there may be one or more instances for this class. And they all share the same principal operation, but providing the service with different costs and different precision. And usually the quality of service providing becoming higher means we need more time to calculate this. And this gives us the freedom to find a solution which provides, under the real-time constraints, the best possible quality. And we are working with periodic and aperiodic tasks, assuming that they all are hard real-time, and making use of the entire toolbox of real-time computing to solve this. What we have to solve is a system, a problem like here. We need, for an adaptation, we may have to add an additional component. We need processor bandwidth for this. At the moment, there might be no bandwidth free, but if we replace one component by another one, which is running at lower quality, but needing less time, we may gain the bandwidth which we need to include the new component. This is how this situation looks mathematically. People in algorithm immediately see what we have to solve. We have to solve a knapsack problem where the constraints are the real-time constraints, and what we want to achieve is, over all the components which we have in the system, the highest overall quality which are within the bounds of our real-time constraints. And if for periodic and aperiodic processes, these requirements look a little bit different, and but I don't want to go through the equation here. Well, now we have our adaptation implemented, but of course in a safety critical system we have to mistrust the result, so we have to check whether the result is correct. And we have, unfortunately, again, some aspects to weave which are not so consistent. So usually if we have anomaly detection, we know what is normal behavior and check whether our system has normal behavior, but we did self-adaptation. So we have autonomous changes. So what we just can say, well, we guess that it is maybe normal, it may be suspicious, or we know that's malicious. And to make it even more complicated, we have real-time systems. So we have very strong restrictions concerning memory usage and runtime. And bringing all this together is what we have to do. In our approach, we abstract it to situations which are really critical, namely the system calls. We can allow our algorithm to do what they want. As long as they are not making a system call, it cannot cause any problems. As whenever it communicates with another process or causes some actuator to do something, we have to make a system call. And therefore, there's a couple of literature saying analyzing a system, the best way of abstraction are sequences of system calls. And but then we have all the necessary parameters and aspects to use artificial immune systems, more precisely danger theory, and map our problem on this field, which is rather well investigated. That's the resulting architecture. I will skip it, and I came to the end. So we have seen that digital twins constitute a natural extension of classical digital design documents. And as they are executable, they span over the entire lifetime of any kind of product, offering any kind of services. So it's a very universal concept. I discussed shortly universal digital twins versus families, and I mentioned 3 possible application areas, and therefore, obrigado pela sua paciência.
Just curiosity.
Composition is with real time is really challenging, isn't it? So, congratulate for your nice presentation. Makes it really clear the problem. What are the best approaches when you have to search in the solution space, trying to find the optimal composition for a given time? We have a specific techniques applied for real time, or use ordinary optimization techniques?
Yes, we are in the area of configuration systems, which again is a well-studied field. And there are various techniques how to configure automatically systems. It's going back decades, the research in this area. And in more recent times, techniques of machine learning are applied to find similarities, to select quickly what kinds of components may fit to the requirements. So this means reducing the search space. So that's, I think, the direction where people are going at the moment.
Any question more? Thank you very much for the nice talk. So I'd like to invite Professor Gabriela Maran, who is never been to Salvador.